Hello, my name is Drouin-Touchette, and I'd like to talk to you about the multiorbital Hund's coupled impurity. This is work that was done at Rutgers University with Yashar Komijani, Elio Koenig, and Piers Coleman. Now, over the years, the role of the Hund's condo has evolved. The Hund's coupling tends to maximize the total spin per site, as is shown in this Hamiltonian here. So if you have coupled orbitals that like to align all of the spins so that they are ferromagnetically aligned on a single site for each of the orbitals. There's a long line of work to understand its role from Schrieffer, Anderson to Yin, Howley, and Cotillard. In particular, for the last authors, they've introduced the notion of Hund's metals. Hund's metals are ones in which the electron hopping is highly correlated with the ferromagnetic state. So for example, in the first site, you could hop from one to the other if the electrons are aligned because it satisfies the Hund's coupling. Whereas in the third example here, if you hopped an anti-ferromagnetically aligned electron, so a spin down electron, for example, it would not like to hop because there's a high cost of JH to do so. This can be seen in the multi-orbital Hubbard model, where the Hund's coupling now is a strong driver for electronic correlation. And there's been a lot of ideas going around for the role of this into the iron-based superconductors. For example, in particular in the iron-based superconductors, there's a universality of the superconducting mechanism. So the gap over the critical temperature, well, the largest gap over the critical temperature has been shown to be about 7.2, different from BCS superconductivity, but over all of the families and all of the iron-based superconductors, a clear number. There seems to be a universal physics at play, and furthermore, they all have this very important Hund's physics because all of the iron atoms sit inside this tetrahedral environment of arsenide selenium with about 2 electrons in the T2G triplet, which is Hund's coupled. So this brings us to the idea that we need quick and scalable and efficient methods that can tackle the multi-orbital impurity problem. And we can use that as an input for DMFT, where DMFT uses an impurity problem and solves itself consistently. So in that retrospect, I'd like to introduce the Hund condo model. Now, this is a model, the way I've written the Hamiltonian here is for M coupled orbitals. For simplicity, we'll take it to be three orbitals together. The first term in red is the Hund's term. This tends to align ferromagnetically all of the spins at each of the orbitals. And in blue, this is the condo term. So in this case, all of the orbitals have a spin that is coupled through the condo coupling to its own conduction bath. All of these conduction baths have a kinetic Hamiltonian that is in the middle as a second term. So there's a competition between the Hund and the condo. The Hund likes to align all of these electrons together, all of the spins together at each of the orbital, whereas the condo would like to create an anti-ferromagnetically aligned singlet between a spin at an orbital and the conduction bath. So this competition leads to multiple regimes, and we can understand them very easily right now, and we'll see later on that they emerge from the simulations. So for example, if the Hund's coupling is much smaller than the condo temperature, the bare condo temperature, then there is just independent screening. Each of the spins at each of the orbitals will be screened independently. But the interesting regime is where the Hund's coupling is now larger than the bare condo temperature. And screening now happens in a two-step process. Firstly, the system, in a high temperature, the system is simply paramagnetic. Here in this pictorial representation, all of the 3 spins at the 3 orbitals are the black ones, and they're coupled with the Hund's coupling via the red dots, the red dotted line, and they all have their own conduction bath, which is the gray lines. So in the high temperature, the system is paramagnetic. The susceptibility is Curie-like with a small moment. And as the temperature is lowered, we hit first at the temperature of the order of JH, another paramagnetic state where the spins are now locked together. So as you see here, all the black spins are now oriented in the same direction. The system has not been screened yet. It's just that we formed a larger moment. There is now still a Curie susceptibility, but with a larger moment. And finally, if we go further in lower temperature, we hit a renormalized, highly renormalized condo temperature, where this larger spin of all of the orbitals together is now screened, and we create the Nozier Fermi liquid and the local singlet. Now we'd like to explore this phenomena and see if we can extract some information about this renormalized condo temperature. How we will tackle this? We will tackle this using a large N Schwinger boson approach. In such an approach, we go in two different ways to decouple the Hund and the condo interactions. So we first decouple the Hund interaction using Schwinger bosons and represent the spin as a combination of Schwinger bosons, whose number is fixed to be equal to 2s, the size of the spin. This constraint will be seen through a Lagrange multiplier, which is the lambda that you can see in my Green's function. For treating the Hund's interaction, we introduce holons. Holons are the brief moment where an electron has left the orbital and has left a hole behind. These holon chi are introduced in the Parcollet-George decoupling that you can see here. And this leads us to two Green's functions that are coupled together using self-consistent equations. So this diagram that you can see on the right is the dominant diagram in the large N picture, N being the size of the group that we use, so SUN. So what we're going to do is we're going to solve these two self-consistent Dyson equations for the self-energy and the Green's function and explore what happens as we lower and lower the temperature. So this is a very quick recipe numerically, and this is why it's a very highly scalable method. What we see for the evidence of the reduction of the condo temperature is, for example, if we look at the phase shift, the electronic phase shift, as the Hund's coupling is increased. In the yellow, the Hund's coupling is practically 0, and as the phase shift goes towards pi over n or pi over 2 in the SU2, it will have the condo temperature, where the formation of the local singlet. And as the Hund's coupling is increased, we see a huge renormalization by 2 decades of magnitude of the condo temperature. And this is also seen in the entropy. So if we look at the entropy, which we can calculate extremely precisely, in the small Hund's limit, as again, the yellow curve, there's only, you go from the high temperature entropy corresponding to the paramagnetic regime down to the down to 0, entropy equals 0 at low temperature through only one jump. Whereas in the large Hund's coupling, there is a 2-step decrease of the entropy, where we go to this temporary stage of the entropy corresponding to free locked 3 spins. So those 3 spins are free corresponding to the conduction C, but they are locked together, and that's a reduction in the entropy. And this can be seen in the specific heat itself, which is something that our method is very capable of obtaining compared to other methods. We can have a clear specific heat profile for the model. So this is for a large Hund's coupling, and we see the 2 different regimes of an orbital condo where the spins have formed this larger impurity together, and then that impurity being screened at a lower temperature. And there's 2 decades of temperature between those 2 specific heat peaks where we have a locked fluctuating moment. And this is something that we can also see if we plot the moment, which is the temperature times the susceptibility. We can see this emergence of this larger moment at temperatures in between. This leads us to a general phase diagram where for high temperature, we have the regime 1. There is no screening. The system is fully paramagnetic. There is a regime 2 where we have now locked moments, and there's a screening of these orbital fluctuations. So the spins are screened. They can still have variation with respect to their conduction C, but we have this larger moment. And finally, in regime 3, the Nozier Fermi liquid, where all the degrees of freedom are screened, and everything goes back to this antiferromagnetic singlet. Very interestingly, we can do a linear fit on this slope of at the left side. And we get something that is very consistent with the approach by Nevedamsky and Coleman in 2009, which does confirm that our large N method is consistent with the RG calculation that was done back then. So what this means is that we have a very clear understanding of the renormalization of the Kondo temperature as the Hund's coupling is large, and leads to this sharp exponential depletion of the Kondo temperature. In conclusion, I'd like to say that this large N method retained all of the physics of the Hund's Kondo. There's a difference in orbital and spin screening. There's this exponential depletion of the Kondo temperature for a large Hund's coupling. For future work, we'd like to explore what the mixed valence regime for this means. So in this, the way we did our work here, there was on average 1 electron per each orbital site. So 3 electrons on the 3 orbitals on the Kondo triad. However, we'd like to tune that to 2 electrons in the Kondo triad so that we are effectively 2 electrons in the T2G environment, replicating the iron-based superconductors. Furthermore, we'd like to see if this can lead to emergent local moments. Well, if these emergent local moments can lead to on-site pairing of the electron. And this could be maybe fertile ground for a triplet superconductor and a universal mechanism. And on that, thank you for your time, and thank you for watching.